we started looking at it. At that time, with no particular focused objective, it was this is a new bright source. Let's get to know it. So that's the kind of science we wanted to pursue with the instrument without any particular goal, just to characterize the source. And we interestingly found these quasi-periodic oscillations shown in the left panel here. This I would call is what we were looking for and what we got. There was a new source, we wanted to characterize it. And its characteristic, most prominent characteristic was these quasi-periodic oscillations. At that time, until mid-90s, quasi-periodic oscillations were quite well known and very well investigated, though not the kilohertz QPOs, with the exoset observatory until that time, but mostly in low mass extraordinary systems with neutron stars. Among black hole sources, I think there are only 2 or 3 sources in which QPOs were detected. So in that sense, this was an interesting discovery, finding QPOs. But however, this didn't surprise us. I mean, we knew that there are black hole sources and some of them show QPOs. What surprised us was finding these interesting patterns of intensity variation in light curve. On different nights of observation, we found very different patterns. This was unprecedented at that time. None of the other black hole candidates had shown this kind of intensity variation. And this was also the early days of the Rossi X-ray timing explorer. So some of these discoveries were simultaneous, hand in hand with RXT. This was a surprise. And this was a surprise to such an extent that when we presented this result in the IUCAA meeting in Kyoto, a famous Japanese scientist actually quite didn't believe it and said, maybe your satellite pointing stability needs to be looked at. This was such a surprise that they thought it's simply because the satellite is wobbling. Okay. At that time, our instrument did not have much spectroscopic capability. In spite of that, we could at least measure how the temperature evolved during this burst, and found that temperature was at its peak near the end of the burst, and the radius of the corresponding emission zone also decreased. And we had interpreted this as evidence of matter disappearing into event horizon of the black hole. And subsequently, GRS 1915 has been investigated in great detail. All these patterns of variabilities, etc., have been, done to death by hundreds of researchers, mostly with the Rossi X-ray timing explorer, but with other observatories as well. So here is one example of what we are looking for on the left-hand side, and along with that, what we got on the right-hand side. This was a surprise. Another similar thing. So here is a picture of those 3 instruments which are flown on IRSP-3, long time ago, about 25 years now. These are very ordinary instruments, but did give us opportunity to look at some very unique sources, like GRS 1915 at its very beginning. One other such example is, this was again late 90s. There were these class of sources called soft gamma ray repeaters. I think only 3 were known at that time. You have gamma ray bursts. Gamma ray bursts occur from different parts of the sky. Never same source shows up twice. But there are this class of bursts which are softer in spectrum, but they would repeat from a part of the sky. So that's why the name soft gamma ray repeaters. And it was proposed that these are magnetas, that is neutron stars with extremely high magnetic field. And then around 97 or 98, 2 such outburst sources during their outburst or the decay of the outburst, one saw pulsations, very clear pulsations, okay, which then gave more confidence that these are indeed neutron stars. And when multiple period measurements were possible for a given source, it was found that the period is increasing, so the sources are slowing down, and the X-ray emission that is seen from these sources could therefore be the rotational energy being brought out. No, sorry, the X-ray energy was not quite, the rotational spin down was not quite sufficient to power the X-rays. It was believed that then probably underlying magnetic energy is being emitted in X-rays. At that time, we didn't know the spectral shape of these sources very well, so it made sense to try to understand their spectral characteristics. So we made observations with the ASCA observatory, and that was the first X-ray CCD in the sky. So one could measure there and characterize their X-ray spectrum very well, having a power law component which dominates, let's say, above about 2 keV, and then a black body type emission which dominates at lower energies below 2 keV. So this I would call is what we are looking for, and we could do successfully. We could do it well. We could characterize the two emission components in this source. What came as a surprise during this observation is that the source on the right hand side, 1E1048.1 minus 5937, our observations, when combined with all the historical observations, we found the source to have significant variation in its spin down rate by a factor of 2 or more. Okay, now that you wouldn't normally expect from a spinning down neutron star, because if the magnetic field is the cause for rotating neutron star to slow down, if magnetic braking is causing it to slow down, then why should there be large variation on that? Okay, this was a surprise. Subsequently, these objects, a whole lot of magnetars and anomalous X-ray pulsars, have been monitored very, very successfully with, again, the RXT satellite. And the second panel, the panel on the right-hand side, the bottom panel, shows that the frequency derivative of this particular star, for example, indeed has a large variation. So what was a surprise in 1998 is, I think, when we made these observations, have subsequently been studied in great detail. But this is not what we had expected when we took up this observation. So these are two examples of non-accreting neutron star systems, where I give you example of what we are looking for, and in addition, what we got, that surprise pair. So now I would go on to talk to you about a whole lot of accreting neutron star systems.
Vishwajit, there is a question for you from Ashwin.
Yeah, sure.
Sir, this is magnetar. Is it isolated? Or
magnetars are isolated objects, yes.
So there is a spin down that is understandable, but what is there any idea as to why it's spinning up?
This is not spinning up. Oh, no, the sources do not spin up. They spin down only, except for some glitches. They are already. You can see the spin down rate. The frequency derivative is always negative. On the right hand side panel, right hand side bottom panel, you can see it's always negative.
Right.
Yeah. Okay.
So it's isolated.
Yeah. Yeah. Okay. So as far as accreting neutron star binaries are concerned, I would talk about results that we have obtained from pure X-ray timing, sometimes from broadband spectroscopy, sometimes with high resolution spectroscopy, sometimes from multi-wavelength observations, sometimes spectrotemporal studies, that is timing studies at different energy bands, or spectral studies at different pulse phases or at different times, and so on, and in some cases very long-term observations as well. Okay, it ranges from studies of orbital evolution using eclipses or pulse timing. Some cases it is studies of the spectral lines in the sources, sometimes the continuum spectral characteristics, and so on and so forth. However, I arranged the talk in slightly different way. Instead of linking the topics in terms of the technique used, I would go subject-wise. So whatever is listed on the left-hand side, we have ordered slightly differently to have some sort of a continuity in the talk. I would start with what is called soft excess in accreting X-ray pulsars. So an accreting X-ray pulsar, a sketch is shown here, where you have a neutron star with a strong magnetic field. The magnetic field stops the accreting material at some distance, the alpha radius, from which the matter follows the magnetic field lines and falls at the two poles. There is X-ray radiation from the polar cap region, and from the accretion column it gets Compton upscattered. Now, this emission is not isotropic. It has some sort of beaming, and because it is spinning around a different axis, not the magnetic axis, the beamed emission would appear pulsed. That's how the objects appear to be pulsating X-ray objects. The X-ray emission from the polar cap region is mostly a power law with a high energy cutoff. If in some sources you do see evidence of cyclotron scattering, cyclotron resonance scattering, which leads to an absorption dips in the or sometimes multiple absorption dips, the fundamental and harmonics and so on. Now the radiation reaches the observer from the polar cap regions. Part of it also gets reprocessed elsewhere in the binary system, And one region, natural region to think of where reprocessing can take place is the inner accretion disk. Okay, and if this radiation causes heating of the inner accretion disk, and then if it re-radiated, the energy of the radiation would be of the order of fraction of a kiloelectron volt. So along with a non-thermal component from the polar cap region, many of these systems, there is also soft X-ray emission, mostly from the inner accretion disk. However, the soft part is not observable in most such systems because many of the HIMARS X-ray binaries are in our galactic plane. Therefore, the soft X-rays like below 2 keV is completely absorbed. To look at this feature with some detail, we picked up some sources which are off the galactic plane, and most favorite objects therefore are in the small Magellanic Cloud and large Magellanic Cloud. We studied SMC-X1 and LMC-X4 with the ASCA observatory to study their broadband characteristics. Hercules X1 is one other very well-known accretion powered X-ray pulsar, which does not have so much of absorption. So one sees this the low energy component, the thermal component in the spectrum very clearly. Most other HIMARS X-ray binaries, we do not see this because it is absorbed. So when you looked at the spectrum of SMC-X1 with the ASCA observatory, we characterized it with a power law component, then a soft thermal component, and so on. That is shown in the left panel. In the middle panel, you see the pulse profile at energy below 1 kV, 1 to 2 kV, and 2 to 10 kV. Now it's very clear that 2 to 10 kV pulse profile is double peaked, whereas the low energy pulse profile is single peaked. So we took up doing a pulse phase resolved spectroscopy. At every pulse phase, we measure the power law component and the blackbody component. Now, statistics in low energy band is not so good, so the blackbody flux measurement has larger error or large variability, whereas the power law flux is constant quite well, and we can still very clearly see that the pulse profile of the blackbody component and the power law component is different. The power law component is the true pulse profile, which is coming from the neutron star. Blackbody pulse profile is the reprocessed emission, that is how the accretion disk is seeing the radiation and how we are seeing that part of the accretion disk which is reprocessing. So this phase difference between the power law component and the soft component is something we were not looking at when we took up characterizing these sources, and this was some sort of a surprise for us, seeing the soft component to pulsate differently from the power law component. Subsequently, this topic has been probed in great detail from quite a few sources using much larger observatories like XMM Newton and Suzaku. And what makes it more interesting for some of these sources is when the source has a different kind of variability. Some of these sources have what is called a super orbital intensity variation. I'll show you what super orbital intensity variation is. In sources like Hercules X1, SMC-X1, LMC-X4, if you see the long-term light curve, you see very interesting persistent patterns. In Hercules X1, it is a 35-day superorbital period. So over every 35 days, there is a almost fixed pattern of intensity variation. In LMC-X4, there is a pattern of intensity variation at about 30 days. And in SMC-X1, it is not a fixed period, but there is very clear periodic variability, not at a fixed period. These are called super orbital intensity variation. And from the very beginning of, when these patterns were known, people had projected what could possibly cause this variation. It's understood to be absorption because all these sources are also eclipsing binaries. So we know that we are looking at the binary at a very large inclination. Now, if the accretion disk is also more or less coplanar with the binary orbit, then the accretion disk might block our view of the central object, or if the accretion disk has a warped structure, that may block our line of sight. Okay. Now, if the warped structure is there in some sources, and if the warped structure precises, that precision period might cause periodic obscuration of the central object, leading to these superorbital periods. Okay. Now, if that is true, and we have also seen that in these sources, the reprocessed emission is actually originating in the inner accretion disk. What would we expect? The central source we are seeing directly. The visibility of the central source changes with the phase of the superorbital period. But the reprocessed emission, which comes from the inner part of the accretion disk, therefore, would have a time lag with respect to the power law component, which comes from the central source. The power law component and the blackbody component originating at the central source and at the surface of the inner accretion disk, there is a light travel time difference. The photon from the neutron star has to go to the reprocessing site, and after reprocessing come to the observer. So if it is in the opposite direction, you would have a time delay which corresponds to twice this light travel time. And if it happens to be in the perpendicular direction, then you would have a time difference which is equal to the light travel time across the radius of the inner accretion disk, and other way. Now, so you would expect a dependence of the phase difference between the soft component and the hard component as a phase of the suborbital period, depending on which direction the structure is visible to us. So people did pick up this topic and pursued with several observatories. In case of LMCX4, I'm showing the results where the red shows the power law component and black shows the soft X-ray component. Okay, and you can see in different phases of the suborbital period there is a significant phase difference, and the phase difference varies between the soft component and the hard component. And these people have also done pulse profile modeling and so on and so forth to close this chapter. That the suborbital variation in these sources does happen because of warp absorption in the warp precession accretion disk, and there is reprocessing from the inner part of the accretion disk, which produces pulse soft X-ray pulses with a different pulse phase. These are results for LMCX4 with Suzaku Observatory, and then with simultaneous observation with New Star and XMM, New Star in hard X-ray band and XMM in soft X-ray band. Again, it has been shown that soft and hard X-ray, there is a phase lag, and the phase lag is the function of the suborbital phase. Okay, so this is almost a settled topic. However, since there are large number of observations of these sources to pursue this particular aspect with both New Star and Suzaku, we thought why not take a look at the spectral characteristics as well, the broadband spectral characteristics. And what would we expect? If the central object is blocked by this structure in the accretion disk at different times, and let me go back to the suborbital intensity modulation in the light curve as well, what you may notice is that the peak of the suborbital modulations is almost constant. Okay, SMCX1 so far about more than 200, I think, such cycles have been seen, and the peak is almost constant. Okay, that would imply in this model that the central object has a constant luminosity. The variation that we are seeing is basically because of absorption. There is no other intrinsic variability in the source. Okay. Now, if we have broadband X-ray spectrum from such a source, we should be able to feed the spectrum. The only difference from one to the other is absorption. Okay. The normalization of the original power law or original continuum, incident continuum, should not have a large variation because the peaks of those suborbital outbursts are nearly same. Okay. However, when you look at multiple spectra, I think we have analyzed 10 plus 6, 16 observations with the 10 with the Suzaku Observatory and 6 with New Star. If you see the broadband spectrum, the variation in this broadband spectrum from one to the other looks nothing like power law being absorbed. Okay, if it's a power law being absorbed, the absorption would be much more dominant in low energy band than in the high energy band. Okay, than what is seen in these sources. That is one thing. Okay, one possibility is that maybe the absorption is not by photolytic absorption. Maybe it is mostly ionized absorber. Okay, so we tried to fit this spectra with an ionized absorber model as well, or a combination of the two. Okay, but you do not get an acceptable fit, nowhere acceptable fit. Okay, so the overall accepted model of the suborbital intensity variation being caused by absorption in a warped precession accretion disk doesn't seem to hold good when you look at the broadband X-ray spectrum of these sources. The most simplest thing that you would expect is it to be a power law by absorbed by different absorption column density. We have something even more interesting in this aspect. If you go back and look at the pulse profile, the hard X-ray pulse profile itself, which is shown in blue color, you can see, for example, this pulse profile and this pulse profile, there is a significant difference in the pulse profiles, right? The relative intensity of the two peaks are not constant. Okay. Now, if the change in the intensity, overall intensity, as a function of suborbital phase is because of absorption, that doesn't give a reason for the pulse profile shape to change. Right? Pulse profile is originated at the neutron star, and if there is absorption, it would get absorbed by same fraction at all pulse phases. So there could be overall lowering of the intensity, but there should not be changes in the relative amplitude of the pulses of the multiple pulse peaks. Multiple pulse peak change in pulse shape would necessarily indicate something happening to the accretion column structure, something happening as a result, something happening to the beaming pattern of the emission. Okay, so this is what we are looking for: a very well established model, quite well accepted model as a description of the superorbital intensity variation. When you look at it in broadband X-ray spectroscopy, we find it not to meet our expectation. Okay, that is one. Second, this observation was done with, as I said, Suzaku observatory and NuSTAR. Now, Suzaku, the low energy instrument, does not have energy resolution to catch the pulses, but the hard X instrument catches the pulses, and on the NuSTAR instrument also. So on the left hand side, I have all the pulse profiles derived from the Suzaku observatory. On the right hand side, we have all the pulse profiles derived from the NuSTAR observatory, and you can clearly see that the relative amplitude of the pulses, of the two pulses, and to some extent the pulse shape, is also variable and is a function of the superorbital intensity of these sources. Okay, and that for me is a very clear indication that the superorbital intensity variation is definitely not caused only by absorption. There is more to it. Okay, most probable seems is superorbital intensity variation is probably caused by changes in mass accretion rate itself. What could be driving it, we don't know. Okay, but when there is change in mass accretion rate, naturally the shape of the accretion column and shape of the X-ray emission beam can change, and that's probably what we are seeing here. Okay, so this is surprise. We were looking for something else, and this is what we ended up with, challenging the existing model for this class of sources. Now, this is where we are talking about, let us say, obscuration of a central source by some absorbing material. Let's talk about when the absorption is full. Okay, when the source goes into eclipse, the main continuum source is completely absorbed, and all that we would be seeing in such cases is reprocessed emission, reprocessing mostly in the wind of the companion star. In HIMARS X-ray binaries, there is very strong wind. So the central object, even if the central object is completely blocked by the companion during the eclipse, the wind surrounding the companion may still scatter and produce some observable X-rays. That is one. Second, it's quite possible that much of the emission lines, like the iron emission line, is produced in a circumstellar material, either the wind itself or some circumbinary material. And that should not change with eclipse of the companion star. So during the eclipse, the X-ray emission lines, like the iron emission line, quite often stands out. So we thought, why not look at all HIMARS X-ray binaries and see can the eclipse spectrum be sort of a diagnostic for the wind structure, wind pattern, wind composition of the companion star. And this is what we ended up with. We looked at a large number of sources, and we see very interesting patterns. Look at this source, LMC-X4. What happens is the entire continuum spectrum goes down by a large factor, almost factor of 100 during eclipse, and the iron line sort of stands out. That is natural if much of the iron line is produced in a large region surrounding the binary. Okay, same is in, for example, in sources like Centaurus X3, where again the continuum goes down, iron lines stand out, and so on. But there are notable exceptions, like this, the first source, 4U1538-52, where the continuum goes down by a factor of about 1.5 decade. The iron line therefore stands out. But what is quite noticeable is that below 2 keV, okay, the source has some soft X-ray emission, and this emission component is not obscured at all. Okay, so this source probably therefore has another region of X-ray emission, which is far away from the binary system, at least to a distance of comparable to the radius of the companion star. Okay, probably this is wind interaction or wind interacting with some accretion wake or something. Probably there is scope for much further investigation. One other source where again it was surprising was SMC-X1. You can see the out of eclipse spectrum shown in blue and the eclipse spectrum shown in red. It goes down by a factor of about 50 everywhere. Okay, there is hardly any iron emission line component in SMC-X1. What does that imply? Probably indicates towards metal abundance of the companion. This probably needs to be probed further. Okay, so that's about eclipse spectrum. And in most of the cases that I showed you, during eclipse, the X-ray intensity falls by a rather large factor. Okay, but not in all. Here is one exception to that. In the left panel here, what is shown are the orbital intensity modulation of about 10 HIMARS extra binary systems. Okay, and you can see during the eclipse, all the eclipses are phase aligned here at orbital phase of 1. During the eclipse, the X-ray intensity of all of these sources has gone down by a large factor. Okay, more than factor of 20 to 100. Here, in this regard, we have an exception. In one HIMARS X-ray binary, IGR J16393 4643, what you see is that the absorption, we can call it absorption dip or eclipse. During eclipse, the X intensity falls down to about 30%, 1/3 of the out of eclipse intensity. It doesn't go to 0. Okay. Now, under what case the X intensity during an eclipse may not go to 0? We do not expect this, because in an HIMARS X-ray binary from the neutron star, the X-ray emission is coming from a region which has a size of only about 10 to 20 kilometers. Okay, and the neutron star is moving with a speed of about few hundred kilometers per second. So neutron star would go, the X-ray emitting region would go behind the companion star in fraction of a second. However, HIMARS X-ray binaries have strong wind. So even before the source is completely eclipsed near the horizon, there could be strong absorption, but that absorption should not show up in hard X-rays. Okay, so here I have the orbital intensity profile in hard X-rays in the top panel and soft X-rays in the bottom panel. We see almost comparable, dip pattern in both of them, going down to about 1/3 of the out of eclipse intensity. So a partial covering, a partial eclipse in an HIMARS X-ray binary is unexplained. We probably would need more detailed spectroscopic observation to try to unravel this mystery. If the source is eclipsed, then the X intensity should actually go down to close to 0, maybe at definitely less than 10% or so. And during eclipse, the iron light should become dominating. And if it is by absorption, then the absorption should be dominant in soft X-rays, and it should be much less in hard X-rays. Okay, so this partial eclipse is a puzzle we have in one of the HIMARS X-ray binary systems. Now I would move on to a different kind of HIMARS X-ray binary system. This is a class of objects that has been discovered about 12 years ago, called supergiant fast X-ray transients. These are also HIMARS X-ray binaries. You have a neutron star going around a massive companion star. But the difference, there are two differences for these sources with respect to the garden variety of HIMARS X-ray binaries, which is these sources are usually about 3 orders of magnitude fainter than the garden variety of HIMARS X-ray binaries. Typical HIMARS X-ray binaries have a luminosity of 10 to 36 to 10 to 37 lux per second, whereas the supergiant fast X-ray transients have intensity of about luminosity of about 10 to 32 to 10 to 34 lux per second. However, every now and then these sources go into a flare, as shown in the light curves on the left. It's the same light curve plotted in different scale, and one is linear, the bottom one is in logarithmic unit. They go into a flare state, which may last from few minutes to few hours. And during these outbursts, they are very much like a HIMARS X-ray binary, the garden variety of HIMARS X-ray binary. So there are two things to explain for these sources. One is their relative faint luminosity, relatively low luminosity by 3 orders of magnitude, and the flaring. Now, flaring may happen if the wind of an HIMARS X-ray binary is wind of a massive star is very clumpy. Okay, occasionally the neutron star may capture a clump and go into a flare. But the overall faint luminosity, overall low luminosity of this class of objects at that time, one possibility was that maybe they have very large orbits. At least few sources were known to have wide orbits. And when you are in a wide orbit, you get to accrete a smaller fraction of the total emitted mass. Okay. However, when we looked at one of these sources for our own reason, we found an orbital period. Okay, and when you folded the data with that orbital period, we found an eclipse. This is not the result that we had published in 2009. At that time, this was taken from Swift Bat Observatory. The data was only of duration of 4 years. Over last 15 years or so, the significance of this measurement has increased, and this is with the current data. If we take all 15 years of data, we find this very clear detection of an orbital period and this orbital profile of the source with an eclipse that lasts about 25% of the binary orbit, very similar to all other HIMARS X-ray binaries. Okay, And the thing to notice is that the orbital period of this source is just 3.3 days. Okay, so this is not a wide binary. Okay, and this happens to be the shortest period supergiant fast exit transient ever known. And there is one more object with a period of close to about 4 days. So one possible explanation for the relative faintness of this object was ruled out from this unexpected discovery of a very short orbital period. And this is not what we are looking at in this system. Okay, and the eclipse also says that we are probably looking at it close to the orbital plane. Something more about this class of supergiant fast exit transients. For some reason, we were looking at the X-ray spectrum of all high mass X-ray binaries with the neutron XM emission and with the Suzaku observatory, both of which have CCD spectrum and very large effective area. What we were looking for are very, very strong iron line. Okay, for example, sources in this panel, okay, has a very large equivalent width of iron line. So here has very large equivalent width of iron line. So the sources which are shown with a white background, the spectra which are shown with a white background, are the ones which are in the garden variety of high mass X-ray binaries, and the sources which are shown with a light blue background are the ones with a supergiant fast X-ray transient characteristic. Okay, now somebody with very keen eye would notice that these objects with blue background are somewhat different from the other, in the sense that none of these sources show very high absorption and none of these sources show very strong iron line. Okay, if we put all the results for all of these sources in one figure, plotting equivalent width versus absorption column density, what we find that high mass X-ray binaries are distributed, shown here in different colors, are distributed all across the panel, whereas the supergiant fast X-ray transients are all lumped together in the bottom left corner, indicating that supergiant fast X-ray transients never have large absorption column density, they never have large equivalent width, even though the type of the component star is identical and the orbital period of these systems are distributed over identical range. So that throws an interesting possibility that are the companion stars in supergiant fast X-ray transients have low mass loss rate, or do they have very high wind velocity? Okay, in either case, you would end up with low column density and low equivalent width of iron line. And this is not what we are looking for when you took up this study of a large class of sources. Okay, so this was a sort of a surprise for us. When you are talking about iron line, let me show you one example of study of iron line with high spectral resolution with the Chandra spectral grating. Here again, we were looking for a very interesting feature that has been seen very clearly in only one X-ray source so far. This is the phenomena of Compton recoil. Okay, now if a source is embedded in a very dense cloud, if an X-ray source is embedded in a very dense cloud, there will be large absorption, there will be production of copious amount of 6.4 keV iron line. These iron line photons will come to the observer, but part of them will also come after scattering. Okay, now complete backscattering by 180 degree can produce a Compton shoulder, okay, a low energy shoulder of the iron line. That's what we are looking for when you targeted, when you carried out this observation of a large number of, or analysis of a large number of data from all high mass X-ray binaries. What we are looking for is sources with extremely large iron line equivalent width and large column density. One source which was known to show very large absorption, variable absorption, however, was GX1 plus 4. And in an observation of this source simultaneously carried out with Chandra and proportional counter array on board RXT, we did simultaneous X-ray spectral fitting. And in the HETG spectrum, we find this interesting feature that it has a 6.4 keV line. Along with that, there is a 6.95 keV line, which is that from Lyman alpha, hydrogen-like iron. Now, what kind of system can have neutral iron and hydrogen-like iron, nothing in between? This was a surprise. We are not, hoping to get hydrogen-like iron in an X-ray binary when there is no other emission line in between. There are sources like Centaurus X3 and so on, where the central X-ray radiation causes a onion-like structure in the ionization pattern. The innermost one will be most highly ionized, and the outermost one will be lowly ionized or neutral. and you would have a distribution of material with different ionization states. And so along with the helium-like lines, sorry, hydrogen-like lines, you also see helium-like lines at around 6.7 keV in Centaurus X3 and a couple of other sources. This is a very rare example along with Hercules X1, where you have a hydrogen-like iron line and a neutral iron line and nothing in between. And this we did further investigation and concluded that this is probably produced from the accretion curtain, where the material is flowing from the Albany radius to the neutron star, but not as a very thin and highly dense flow. It has to be sufficiently diffuse to have sufficiently high ionization parameter to produce this line, but not produce the helium-like line. So this is what we ended up with when we were actually searching for this tiny shoulder on the iron line, which is the Compton Recoil feature. Okay. Okay, so now let me give you one glimpse of multi-wavelength study for HAMAS X-ray binaries. So these iron lines are very narrow spectral features in HAMAS X-ray binaries, and very narrow timing features are the thermonuclear X-ray bursts. Okay, a neutron star of low magnetic field strength, if it is acting at a moderate rate, okay, not a very high accretion rate, and the distributed material is distributed on the entire neutron star surface, then there is a sufficient amount of matter piled up on the surface of the neutron star. It goes through unstable burning, and that suddenly produces a thermonuclear flash on the surface. The rise time of this flash is of the order of a second or so, and then it decays with about time period of about 10 seconds or so. And there is very interesting patterns in them. A flash like this in X-rays from the compact star allows you to study the reprocessing environment around it, which could be the accretion disk, which could be the surface of the companion star, by looking at the echo. Okay, and the echo would be in a different energy band. So there is interest in looking at these thermonuclear X-ray bursts simultaneously in optical, infrared, and ultraviolet as well. Unfortunately, there has been only one observation of a thermonuclear burst simultaneously in multiple other bands. Okay, that is this second burst that is shown here. And people try to understand the region where the X-ray burst gets reprocessed. And what do you expect if you have such an observation? Depending on the phase of the binary, that is whether the neutron star, the companion star is on the side of the neutron star, or whether it is towards the backside of the neutron star, or at some other phase. If the companion star is behind the neutron star, then you expect the reprocessed emission to be strongest because you have a good visibility of the surface. And if it is towards you, then you do not expect much reprocessed emission. So the reprocessed emission, relative intensity of the reprocessed emission, and any time difference of the reprocessed emission with respect to the X-ray and its orbital phase dependence could tell us the origin for this. So what would one expect? If the much of the reprocessing is from the accretion disk, then you would expect this vertical shaded region as the time delay between the X-ray and the optical burst. And if much of the reprocessing is from the surface of the companion star, then you would expect this curve as a function of orbital phase, the delay of the optical or infrared with respect to the X-ray. Okay. So we took this unique observation of this source, this particular source, EXO0748-676. There was a very, very long observation of this source with XMM Newton, with the aim to find gravitational redshift of emission lines from the surface of the neutron star. Okay, but XMM Newton gives something, there is a bonus, because it has a small optical monitor as well. So whenever you look at the X-ray light curve, you simultaneously see the optical light curve. Okay, and out of these 77 thermonuclear X-ray bursts which occurred during this long observation, we found optical data simultaneously in 63 of the bursts, and the optical burst was detected in all 63 of them. We wanted to look at the relative phase, relative time difference between the two, and relative strength of the optical emission as a function of orbital phase. We didn't find any clear pattern, so this data didn't give us what we were actually looking at. But we had some surprises. Okay, look at this burst number 46. The bottom curve is the X-ray burst, the top curve is the optical burst, and the optical emission is delayed by almost 8 seconds. Okay, and if you look at this binary system, which has a time difference, that is size of the binary orbit, the size of the binary orbit is just about 1 light second. So in a binary system which has a size of only 1 light second, it's very unclear what can possibly give an 8-second time delay between the X-ray flash and the resultant optical flash. Okay, so this is surprise but unresolved. Now I would move on in the last part of my talk to primarily timing analysis of data. One that is somewhat clumsy, somewhat difficult to do is pulse arrival time delay study in binaries. It's just a lot of hard work. Okay, but what we do here is, for example, here is result for Centaurus X3. You have the neutron star pulsating with a period of about 4.8 seconds. It's going around in the binary. So if you catch the arrival time of the pulse, you will see a modulation in the arrival time of the pulse depending on where the neutron star is in the binary. Okay, so this can be measured with very high accuracy because this is a bright source, and it can be measured several thousand times in every orbit, and this is what we end up with. Okay, so now once you have this pattern, you can measure the phase of this orbit. Okay, like when the neutron star was farthest away from us or when the neutron star was closest to us. And if you are patient enough and keep track of this over decades, what you find is the, let us say, what you call it the mid eclipse time as a function of time. Okay, and if you take out a linear component, whatever residual is there, that tells us if the orbit of such a system is evolving. Okay, so we have measured the orbital evolution of many HIMARS X-ray binaries. I mean, what I mean is that we carried out the analysis of data of the last 2 decades or so, and combined that with all the previous measurements which are reported. Okay, and these are the current known status of orbital evolution of HIMARS X-ray binaries. The surprise here is that in most of the system, the orbital time scale is at least an order of magnitude smaller than what would happen if the evolution is driven by mass loss from the companion. Like, what is the most dominant process? It is the mass loss from the companion star. And that should give us an evolution time scale of about 1 million years to 10 million years. Whereas we find most of these sources evolving away at a much faster rate. Okay, and in couple of sources we have refuted earlier claims of rapid orbital evolution, like in this source 4U1538-52 and 4U1700-37, just by doing very careful analysis. Okay, earlier there were claims of very rapid orbital evolution, and what we established is almost an order of magnitude smaller than that. So what is interest in the orbital evolution of HIMARS X-ray binaries? What we find is that, or what we think is that, if the sources are evolving away at a much faster rate, then given the number of HIMARS X-ray binaries today in our galaxy, there must have been a much larger number that have evolved away in the past. Okay, then the question arises is, are these the progenitors of some of the double compact binaries? For example, when the companion star explodes in a supernova, that will leave behind another neutron star, and if the kick velocity of the neutron star is in favorable direction, then it may survive as a double compact binaries, and eventually these objects would evolve as evolve and merge and produce gravitational wave and short gamma ray bursts and so on and so forth. So this rapid evolution of the HIMARS X-ray binaries probably is an important number to be used when one tries to calculate the number of double compact binary systems that we may have in our galaxy and other galaxies, which could eventually be interesting sources or potential sources for double neutron star merger for gravitational wave and short gamma ray burst. Okay. Now we'll move on to LOMAS X-ray binaries orbital evolution, and there we have, I'll start with another source where you see partial eclipse. These are the only 2 known X-ray binaries in which we have partial eclipse. One HIMARS X-ray binary I showed earlier, and this is a LOMAS X-ray binary. You can see various orbital intensity modulation curves from different observations, and you can see these eclipses lining up. These are partial eclipses, somewhat odd shaped, but this is understood in this source. It is a neutron star X-ray binary in a LOMAS system where the neutron star has an accretion disk corona shown in light blue here. Sorry, yeah. And if this coronal source is sufficiently large in comparison to the companion star, then it is not going to be fully eclipsed. Okay, it will only be partially eclipsed, and the partial eclipse is what is seen here. And because of this accretion disk corona, much of the emission that we see from this source actually comes from the corona. Only a tiny fraction is the original emission from the neutron star. As a result, it has a very small pulse fraction. So this is also a pulse source. So we study the orbital evolution of LOMAS X-ray binaries using multiple techniques. One is using the pulse timing, which is done for this source, XTJ1808-5635, and Hercules section, which is shown on the right. It is done with eclipses, partial eclipse in case of 1822-37, and full eclipse in case of several other sources. Okay, so I will go into details of some of these studies. One thing to say here is that in low mass X-ray binary system, if the orbital evolution is driven by mass transfer alone, then you expect the orbit to evolve. Okay, but that evolution time scale, given the X-ray luminosity and the mass transfer rate, is much larger than what is actually seen for real systems like these two shown on the left panel. Okay, so there is something beyond just orbital evolution by mass transfer. Probably wind loss from the system, either from the accretion disk, is a main reason for orbital evolution. More interesting are these sources. Two shown in the middle are the ones where you have orbital decay. Okay, you can see there is a negative curvature of this, and three sources shown on the right hand side show glitches in their orbital period. Okay, so glitches are very difficult to understand, and in an orbital period, and the middle ones which show orbital decay probably throws interesting questions. So let me get into some details of these results as well. This source XTJ1710-281, here on the left hand side, eclipse is shown. As you can see, that the eclipse is very sharp because low mass X-ray binaries do not have much wind. The neutron star emission region is only a few kilometers in size, and it's moving with a velocity of several hundred kilometers. It goes behind the companion in a jiffy. Okay, the eclipses are very sharp, and when the eclipses are sharp, you can measure the middle of the eclipse very accurately. And when you put together a large number of such eclipse measurements and subtract a linear term, you end up with this kind of piecewise linear distribution of the residual. Okay, which basically shows that there are glitches, and this source at least had two glitches, and one other source that I showed previous view page here, you can see had at least 1, 2, and 3 glitches. Okay, so glitches in low mass X-ray binaries, what causes them, we don't know. I don't have a favorite hypothesis for that. However, while studying the orbital evolution in low mass X-ray binaries using eclipses, we came across this very interesting source. This is, however, a transient. Okay, I think in early 90s there was one transient outburst, and in 2010 or so there is one more such outburst. Okay, these are the long-term light curves. So if you see during these outbursts the X-ray intensity of this source, it shows a very clear eclipse. The orbital period is few hours, and the eclipses are shown in the bottom in greater detail, one from RHT-PC observatory and one from XMM Newton observatory. And you can see that the middle of this eclipse can be measured very accurately. Now, when we put together a large number of these observations, measurement of the eclipses, and subtract a linear term, we ended up for this source with this long-term orbital decay. But more interestingly, from the RHT era, when there are a large number of observations, we see a somewhat modulating pattern. Okay, and this modulating pattern, if you fit the fit which extends to the most recent observation in 2015, it even goes through that. It also connects well with that data. Okay, most obvious interpretation for this is probably that this is an X-ray binary which has a third object as a companion, and this binary, or the third object, is moving around the binary. The binary is also going back and forth. And that back and forth shows up in terms of a wavy residual in the eclipse timing of these sources with a period of about, I think, about 2 years. Okay. So when you put together these two numbers, the amplitude of this modulation and the period of these modulations, you get the mass and distance of the third object. It turns out the mass of the third object is about 25 Jupiter masses, and it is at a distance of about 800 light seconds. Okay. So one interesting thing is that if this is indeed true, then all subsequent observations of this source should also show this modulation pattern. And that's what happened with subsequent observations carried out with the XMM Newton observatory during the most recent outburst. It was found that this modulation pattern actually continues. Okay, so this indeed has a third object as a companion, which turns out to be about 25 Jupiter mass companion star. So this is a very massive circumbinary planet around this X-ray binary system, and this indeed was a surprise. We never thought of finding a planet by X-ray eclipse measurement. So interesting aspects of this is the first planet around an X-ray binary, first known planet around an X-ray binary stellar system. It's the most massive among all circumbinary planets known, about 8,000 times that of Earth. This is the most compact of all binary systems around which planets have been found. This is the first planet found using X-ray observations, and this is a new technique, the periodic delaying X-ray eclipses. These are the aspects of it. So what interesting thing this throws up? Circumbinary planet formation and their migration, okay, is a different topic than planet formation and migration around isolated stars, around single stars. Okay, so in that class of sources, this is one of the extreme examples where you have a very massive planet around a low mass exabinary, and it also throws up one other question, because as you may notice, in low mass exabinaries we expect a positive orbital evolution, whereas we do find this object and several other objects to have a negative orbital evolution. So the question is, are the negative orbital evolutions driven by the planet? Is the planet gaining angular momentum and going away, and the binary losing angular momentum and coming closer to each other? If that is true, then that may actually be true for several other black hole binaries as well. Now, in black hole exabinaries, it's not easy to measure orbital evolution, because you don't have a pulsating source. Unless the source is eclipsing, you don't have a very good marker for the any phase of the orbit. So one has to do it very painstakingly. That is by measuring the Doppler shift, Doppler motion of the companion star. Okay, and that's how mass function of these objects are determined. So the top panel shows the Doppler shift measurement of a large number of measurements in one such binary systems, from which you measure the orbital parameters and also orbital epoch. And if you do that for several decades, you end up with you ended up with a negative orbital evolution, that is orbital decay, in at least 3 such black hole binaries. Okay, and one doesn't know what can cause orbital evolution of such a system. So naturally, finding this planet around the neutron star system then throws up a question, that are orbital decay of neutron stars and black hole binaries with low mass companions driven by planets? Okay, is it possible that these black hole systems have planets as well? Right. So this, I think, with this I will conclude all the surprising results that we had in accreting neutron star systems. I would say that, while we are trying to improve our knowledge about the systems that we study, most often that is in the form of incremental small steps. We are basically try to polish a surface, but while trying that, we often dig a hole. We find a new problem. Sometimes the problem we have ready answer. Sometimes we do not. I would say this, finding a massive circumbinary planet was a very, very pleasant surprise. So let me, end this with a few slides on what are we expecting in the coming years, and will there be surprises there as well? Okay, as Somo pointed out in the beginning, that we are working towards an X-ray polarimeter instrument, because all results that I talked to you about are on X-ray timing or X-ray spectroscopy or spectral timing, and so on and so forth. There was no polarization element. That's what we're trying with this new instrument. It's a Thomson X-ray polarimeter. It measures X-ray polarization using Thomson scattering. Sorry, the energy band is actually 8 to 50 kV, not 5 to 50. You have a scatterer onto which X-ray radiation from an object falls through a collimator, and the scattered radiation is detected by X-ray detectors on both sides. And this whole instrument is spun around the beaming axis. We hope to measure X-ray polarization using that. This is going to go on a satellite which is named XPOSat, X-ray polarimetry satellite. This is the main instrument, along with another X-ray timing and spectroscopic device, small solid state detectors. And this would be looking at about 24 persisting X-ray sources and whatever number of transient X-ray sources we can catch during the lifetime of this mission. I would just show you one slide. These are some pictures of the instrument that is under development. We are hoping to launch it in the middle of next year. So I would end with one slide on what are we hoping to study with this instrument. It is the X-ray radiation from a neutron star, which is an isotropic, which is beamed, and that gives us pulses. Now, we do not have very clear idea about, for example, what causes this beaming. Is the beaming in the forward direction like a pencil beam, or is the beaming in the equatorial direction like a fan beam? Okay, and the polarization signature for a pencil beam or a fan beam are very clearly different. In case of a pencil beam, at the peak of the pulse, we are looking along the magnetic field line, so we do not expect a high degree of polarization. Whereas in case of a fan beam, at the peak of the pulse profile, we are looking perpendicular to the magnetic field direction. So one expects a very large degree of polarization. Okay, so pulse phase result polarization measurement would establish the beaming pattern of the sources. And if we study, for example, the beaming pattern at different luminosities, that would tell us, for example, how the accretion column structure and therefore the radiation pattern from such sources change with luminosity. And there are many other related topics to be studied, not only in neutron stars but also in black hole binaries. But this is what we are expecting. Okay, but as I told you, in the last 2 decades, while studying various sources, what we expected and what we ended up with was quite often very different. And what we ended up with sometimes was a surprise, and sometimes we had explanation for this, and sometimes we didn't, which would therefore require further investment of time and effort to understand. So I would end with that. I hope you found it interesting, and I hope that not only what we are expecting with this police instrument, we have some unexpected results as well. Thank you.
Thanks very much, Vishwajit. That was a fascinating talk, a very unusual talk, concentrating on surprising results. This is very nice. Wonderful. I'm glad that you didn't preempt all the surprises that you will get, because then it won't be surprises anymore. Any questions? Please raise your hand in the participants window. People who have questions, go to the participant window. There's a raise hand button. And the first question is from Rituban Chatterjee. Rituban, go ahead. I've unmuted you.
Hello, Vishwajit, can you hear me?
Yes, yes, very clearly.
Yes. So I was wondering in this partially eclipsing system, are there optical observations in the optical or infrared bands to which corroborates the observations in the X-rays? I mean.
Okay, in high mass X-ray binary, we would not expect to see anything along with the X-ray eclipse, because in high mass X-ray binaries, the radiation is dominated by the companion star. Okay, that is about 100 times brighter than the accretion disk emission. So I would not expect along with the X-ray eclipse, any emission from the accretion disk also to be shown very prominently in orbital intensity profile. The low mass X-ray binary system indeed shows simultaneous optical dip as well. I do not recall whether that is also partial or not.
Okay.
In low mass X-ray binary system, the optical emission is primarily from the accretion disk. It's much larger than emission from the companion star. So you do see that dip in optical as well.
Okay. Thank you.
Great. Thanks. Next is Dipankar. Unmuted. Go ahead.
Hello, Mr. Can you hear me?
Yes, yes.
Okay, very good. Excellent talk. Fantastic collection of results as usual. My question was related to superorbital period.
Okay.
So it could, given the evidence that you have presented, it could also be that the neutron star itself has a precession and slow precession, and at different phases of the superorbital period, you're seeing at different angles with respect to the spin axis. Now, is there anything to rule that out? Of course, polarization measurement of this would be very, very interesting.
Sure.
But as of now, is there something that can rule that out?
Neutron star precessing.
Let's say Hercules X1 neutron star precessing with 35-day period.
Okay, okay.
So,
so if the overall intensity variation we are saying it's not an overall intensity variation, it's just our visibility of it.
That is correct.
In addition to the pulse emission, there is an modulation on the pulse average emission also. What fraction do we see?
Yes.
Then probably the overall environment of the neutron star, a larger reprocessing region, probably does not see that modulation.
Yep.
So one can probably look for it in the reprocessed emission. Like, if there is strong iron line, maybe the iron line modulation or iron line should not have any flux modulation along with the
Yes,
superorbital period.
that is correct.
So something like that can be thought of and proved, yes. But I'm not sure whether that will be a conclusive evidence or not. One can probably at least look at that.
Yeah. Good. Thank you.
Great. So next question is from Desh. Desh, go ahead. Unmuted you.
This is in fact exactly following on Deepankar's question, just wanted to add a comment that would the pulse shapes reflect the precision of the compact object more readily?
Okay, so there is some effort going on in that direction. X-ray pulsars unfortunately have such broad pulse profiles that, and when you go for X-ray pulse profile modeling, there is so much unknown there. Like, the beaming pattern from the source, then at least two orientation angles and so on, whether you are getting emission from both the poles or not. So all of these factors come into picture, whereas the pulse profile is rather simple. So pulse profile modeling in X-ray pulsars, I would say, hasn't probably been a very sure shot method of getting anything. But there is an effort going on. There is this group that has modeled large number of pulse profiles for single sources from multiple observations. And in spite of pulse profile variability, there is claim that they get consistent values of the angles. That is the orientation of the spin axis with respect to a line of sight and angle between the magnetic axis and spin axis. So for SMCX1 or for these sources with superorbital intensity variation, if we do find that one gets consistent result in pulse profile modeling and the angle between the spin axis and our beam axis changes from as a function of superorbital phase from observation to observation, I think that would be a very useful thing to toward in that direction. So that there is some effort going on. We may hear something in the future.
All right, thanks.
Great, thanks. I don't see any other question. Let me quickly ask you one. I didn't actually get my head around the iron K line that you had, 6.5 keV, along with the Lyman alpha like 6.9. Now, when you have iron K line, you often have 6.4, and then, I mean, at 6.7, 6.9, there are other lines there as well. So
yes,
this is
no.
not, I mean, is it unambiguously you're getting the Lyman alpha line, not other iron K lines?
In this case, yes, because this is a measurement with the HETD, which has very sharp, very high angular spectral resolution. In most high mass X-ray binary systems, you basically see the 6.4 kV line only, and it is quite sharp, except in a couple of cases like 4U1626-67, where the line is actually reprocessed, or there are neon lines and oxygen lines which are produced in the inner accretion disk, and therefore you see the Doppler velocity width and probably some thermal width as well. Most other sources, 6.4 kV line is narrow. There are few sources like Centaurus X3, where along with 6.4, which I think is produced from up to about 16 times or 17 times ionized iron. Along with that, you find helium-like iron, that is a emission line complex around 6.7 kV, often not distinguishable with the CCD spectrum or even getting spectrum. And then 6.95 kV is the Lyman alpha, and then 7.1 kV is the K beta. Sometimes you see 7.4 kV nickel line and so on. Here, I think identification of the second line as 6.95 kV, even though it's not very highly significant measurement, is unambiguous because it's getting resolution.
Oh, yeah, Chandra has the high resolution, of course. That's great. Thank you. Anybody else has any other questions? If not, let's thank Bishwajit again for a fantastic talk, and we'll